Let us solve one or two problems involving speed control of DC shunt motor. For example, let us take a DC motor whose rated terminal voltage Vt equal to 240 volts, the armature resistance equal to 0.04 ohm, the intrinsic field resistance without any additional external resistance Rf equal to 100 ohm. This motor runs at a speed of n equal to 1200 rpm while taking a load current of 200 ampere from the supply. Suppose we want to increase the speed to 1500 rpm. How much additional resistance Rfe is needed for this? Let us try to solve this problem. So, this is the arrangement, DC shunt motor. This IL 200 amperes, supply voltage is 240 volts. Therefore, IF equal to 240 volts by 100 ohm equal to 2.4 ampere. IA equal to IL minus IF equal to 200 minus 2.4 equal to 197.6 amperes. Now, the back EMF E equal to Vt minus Ia Ra. Since at 1200 rpm and 1500 rpm Vt and Ia remains same, the E also remains same. So, this E comes to 236.077 volts and remains constant. So, but E at 1200 rpm divided by E at 1500 rpm is equal to field flux at 1200 rpm into by field flux at 1500 rpm divided by 1200 by 1500, but we know that these two E are same. So, this is equal to 1. Hence, field flux at 1200 rpm divided by field flux at 1500 rpm is equal to 1500 by 1200 is equal to 5 by 4. But field flux is proportional assuming linear magnetic circuit. So, field current at 1200 rpm and field current at 1500 rpm, this should be equal to 5 by 4, but field currents are inversely proportional to the field resistance with constant supply voltage. So, this is also equal to total field circuit resistance at 1500 rpm divided by field circuit resistance at 1200 rpm, but we know at 1200 rpm no additional field resistance has been included. So, Rf 1200 equal to 100 ohm, hence Rf at 1500 rpm should be 5 by 4 into 100 equal to 125 ohm. সুতরাং additional resistance Rfe equal to Rf 1500 minus Rf 1200 equal to 25 ohm. So, we need to insert a 25 ohm resistance in the field circuit in order to increase the speed from 1200 rpm to 1500 rpm, while the load current drawn by the motor is 200 ampere. Now, suppose the load current reduces to 100 ampere, what happens to the speed with this additional resistance in circuit? So, at IL equal to 200 amperes, E is equal to Vt minus Ia Ra, Ia equal to 197.6 amperes, If equal to 240 by 125 amperes minus, so Ia equal to 200 minus 240 by 125 amperes is approximately equal to 198 amperes. So, E is approximately equal to 197.6 volts. And when IL equal to 100 ampere, E is 98.08 to 0.04 ohm. This comes to approximately equal to 232 volts. This comes approximately equal to 236 volts. So, since the field flux is same, N at I L equal to 100 divided by N at I L equal to 200 is equal to E at I L equal to 100 divided by E at I L equal to 200. This is equal to 236 by 232 approximately equal to 1.02. So, N at I L equal to 100 ampere equal to 1.02 into 1500 approximately equal to 1530 RPM. So, there will be a 30 RPM increase in speed if the load current decreases from 200 ampere to 100 amperes. So, another thing we observe that with field control the speed regulation is rather poor. Even for half load reduction, there is a change in 30 RPM of speed, which is not desirable where tight regulation of the motor speed is required. Now, let us try to solve another problem regarding the Leonard method of speed control. For this, let us say we have a Leonard system of speed control with the following rating. There are two identical DC machines. Both are the following rating: Vt equal to 230 volts. The power rating is 4.5 kilowatt. Rated speed is 1500 RPM. The armature resistance of both machines are 0.5 ohm. The magnetization characteristics of the machines at 1500 RPM are as follows. At no field current, there is a residual voltage of 45 volts, 0.2 ampere, there is 110 volts, 0.3 amperes, 148 volts, 0.4 amperes, 175 volts, 0.5 amperes, 195 volts, 0.6 amperes, 212 volts, 0.7, 23 volts, 0.8 to 30 volts, and 1.0 to 41 volts. Now, the IFM is set at 0.8 amperes. The motor speed has to be changed between 300 rpm in motor and 1500 rpm. Over the whole range, the output power of the motor will be 4.5 kilowatt. So, what should be the range of generator field current? So, from this data, when IFM equal to 0.8 ampere, the induced voltage, induced E of the motor is from the OCC data, it is 230 volts. And so, for motor speed Nm equal to 300 rpm, this is at Nm equal to 1500 rpm. At Nm equal to 300 rpm, Em at 300 rpm will be 300 by 1500 into 230 equal to 46 volts. The power output Pm at 300 rpm equal to 4500 watts. So, this is equal to Em at 300 rpm multiplied by Ia at 300 rpm. So, Ia at 300 rpm is 4500 by 46, which is equal to 97.8 amperes. So, what is the generator voltage? Eg equal to E of motor plus drop across both the armature resistance of the motor and the generator. So, 2 times Ra Ia, this comes to 46 plus 2 into 0.5 into 97.8, this gives about 143.8 volts. Now, from the magnetization data, we see that at 0.2 ampere of field current, the generated voltage is 110 volt, and at 0.3 it is 148 volts. So, in order to generate a voltage of 143.8 volts, somewhere close to 0.3 ampere of field current will be required, and this can be found by interpolation. So, the field current required IFG will be equal to, it will be less than 0.3 ampere minus 0.1 divided by 148 minus 110. 0.1 is the difference between this field current and this field current into 148 minus 143.8. This is equal to 0.29 amperes. Similarly, for Nm equal to 1500 rpm, Em in that case we know equal to 230 volts. So, Pm equal to 4500 watts. So, Ia equal to 4500 by 230 equal to 19.6 amperes. So, E generator equal to 230 plus 2 into resistance of the armature, which is 0.5 ohm, into 19.6, this is equal to 249.6 volts. Now, again from the magnetization characteristics we find If the missing data, which says for 1.2 ampere this is 251 volts. So, point minus 0.2 divided by 0.2, assuming linear, this is equal to hence for 300 IFG will vary in the range 0.29 to 1.18 ampere. So, this is how we can calculate the field current required from the generator of a Leonard system for controlling the speed of the motor over a given range. So far, we have concerned ourselves with starting and speed control of a DC shunt motor. However, the stopping of the motor is also equally important. So, let us see a few cases where this stopping becomes controlled stopping becomes very important. Let us go back to the situation of the lift or elevator drive, where as we have mentioned, that is this elevator cage the weight of W C g, and then there is a counterweight of W C c C w. In order to lift the cage, this is omega for upward motion and this is omega for downward motion. So, the motor shaft needs to rotate in two different directions. Now, let us see what happens under different operating scenario. This is for upward motion, this is for downward motion. Suppose the cage is full, so that WCG is larger than WC, and we want to lift the cage. In that case, we have seen that the torque speed characteristics of this machine, this system is given by a vertical straight line, and if it is driven by a separately excited DC machine, then somewhere here the operating speed will be. However, as the destination approaches, it is necessary to stop the machine, but there was already some speed of the motor and speed of the system. So, the stored kinetic energy has to be dissipated. So, it is necessary to apply certain braking torque, so that the motor speed comes to standstill, that is, for some time the motor should be allowed to decelerate. This is achieved by what is called dynamic braking, in which case the terminal voltage of the motor is made 0 and the additional resistance is inserted. Hence, the motor characteristics becomes somewhat like this, and when you go to that, then the operating characteristics shifts to here. So, in addition to the load torque, a amount of braking torque is applied, which quickly stops the system. This is one situation. Another situation may arise where in this case, suppose I am trying to lift a empty cage. Previously I was lifting a full cage, now I am trying to lift a empty cage. Now since now WCG is much lower than WCW, the torque speed characteristics of the load will now shift to, will become negative, will go in this direction. Now the same motor torque speed characteristic is the same applied voltage, it will remain the same. Now we see that the operating point shifts to second quadrant, that is the motor. Now machine now acts as a generator and produces generating mode torque. The machine runs at a speed somewhat higher than its no load speed and feeds power back to the supply. This is called the regenerative braking mode of operation. It should be noted that the regenerative machine mode of braking, the motor will normally run at a speed higher than the rated no load speed. Hence, it is not possible for the regenerative braking mode of operation to bring the motor to a standstill. It will continue to run at a speed higher than the rated no load speed until and unless, of course, an arrangement is made to bring the applied armature voltage, reduce the applied armature voltage gradually to 0, in which case even regenerative braking method can be used for stopping the system. A third situation will arise. Suppose we are trying to lower a full cage. The direction of rotation will now be this. However, it is necessary to lower the cage since WCG is now larger than WCW. The load torque is in this quadrant. However, now the motor rotates in the reverse direction and it is necessary now to control the speed, in which case what we do, we reverse the terminal supply and make the motor operate in this fashion. So, this becomes the supply voltage. So, there are different methods of braking a DC shunt generator, in which one case we found that this is called the regenerative braking. Here the load tries to drive the motor at a speed higher than the no load speed, this is motoring, and this is the regenerative braking mode of operation. At a speed higher than the rated no load speed of the machine. So, the motor works as a generator, and hence a opposing or a braking torque is generated, which tends to limit the speed of the machine. It should be remembered that regenerative braking cannot be used for stopping the machine. The other braking method or stopping method is called the dynamic braking method. In this case, the motor is disconnected from the supply and then connected to an external braking resistance. So, again the motor acts as a generator, and the kinetic energy stored in the motor and load system is dissipated in this resistance. And let us say that while motoring, it was operating on its normal torque speed characteristics at a speed of omega, and in order to apply regenerative braking, we disconnect the machine from the supply, hence the applied terminal voltage becomes 0. In addition, we put additional braking resistance Rb. So, the characteristics now becomes a straight line passing through the origin, the slope of which is determined by the braking resistance Rb. So, as soon as dynamic braking, this is motoring characteristics, this is dynamic braking characteristics. The motor torque speed characteristics is omega equal to Vt by k phi minus Ra divided by k phi square Te. The motoring mode Vt was equal to Vt rated and Ra was equal to armature resistance of the machine, and this was the characteristics. During regenerative braking, Vt is made 0, then the characteristics becomes minus Ra plus an additional resistance Rb is added, Rb by k phi square Te. So, as the speed goes down, or in other words, the torque generated by the machine becomes minus k phi square by R A plus R B into omega. So, as soon as regenerative braking is applied, the operating point shifts from point A to point B, since the speed of the machine cannot change abruptly, and then it follows the regenerative braking characteristics and comes to standstill. So, this is called the regenerative method of braking. In this case, the motor can be made to stop completely by electrical braking method, but it cannot recover the stored energy in the machine and the load back. So, this energy is wasted in a braking resistance. It is important to add a additional braking resistance, because otherwise the current during regenerative braking can be very large, as much as the almost the starting current with direct online starting, which is not desirable. Therefore, additional braking resistance is normally included. There is a third method of braking called plugging. In this case, what we do, it is somewhat like dynamic braking. But this is the position of the switch for motor mode operation, this is the position of the switch for plugging mode operation. So, what we in essence are doing is, in order to apply plugging, we disconnect the machine from the normal supply and reverse the polarity of the supply voltage. It is of course essential that a additional resistance is inserted into the motor terminal. So, what will be the characteristics? So, this was the nominal torque speed characteristics of the motor. And suppose it was operating at the speed of omega 1. When we apply plugging, the polarity omega equal to V t by k phi minus R A by k phi square T E. For plugging, the polarity of V t is made negative, as well as R A increases to R A plus R P. So, for plugging, the characteristics become somewhat like this. And as soon as plugging is applied, the operating point shifts to omega 2, and then follows the, this is the motoring mode, and this is the plugging. And then follows the characteristics during plugging to come to 0 speed. However, it is to be understood that if we apply plugging, then the motor can have a larger braking torque, but it does not stop at 0 speed, rather it tends to start rotating in the reverse direction. Therefore, before the motor come to a standstill, it must be disconnected from the supply, otherwise the motor may start rotating in the reverse direction. Another thing to note is that during plugging, the polarity of the, as long as the speed remains positive, the equivalent circuit of the motor becomes somewhat like this. This is the plugging resistance, this is the armature resistance, and this is the induced back EMF. The polarity of the supplied voltage has now reversed, this becomes plus, this becomes minus, V T E. The current I A now flows out of the machine, I A equal to V T plus E A divided by R A plus R P. So, not only does the power supplied by the internal back EMF E P, but as well as the power, additional power is taken from the source, which is also dissipated in the armature and the plugging resistance. So, this method of stopping the motor is very inefficient and is not used except for very small motors. Let us try to get an idea of the kind of power loss that is involved by solving a small problem. For that, let us assume that we have a DC shunt motor, rating is 220 volts, 970 RPM, 100 amperes. The armature resistance R A equal to 0.05 ohm. Suppose we want to break it by using plugging. from a initial RPM of 1000 RPM. So, find out what should be RP so that IA maximum is less than 2 times the rated armature current, hence it is less than 200 amperes. Then what is the braking torque? And what is the torque at 0 speed? Now, at 970 RPM, we know at rated current E equal to 220 minus 0.05 into 100 equal to 215 volts. So, at 1000 RPM, equal to 1000 by 970 into 215 equal to 221.65 volts. So, if I want to restrict the current to 200 ampere, then RP plus RA equal to E plus V divided by IA, this is equal to 221.65 plus 220 by 200, this is equal to 2.21 ohm. Hence, RP will be 1.16 ohm. The braking torque TE plugging equal to E into IA by omega, this comes to 423.3 Newton meter. So, very large torque. At 0 speed, E equal to 0. So, IA equal to V divided by RP plus RA, this comes to 99.55 amperes, and since T is proportional to IA, TE at 0 will be equal to 423.3 into 99.55 by 200, this comes to 210.7 Newton meter. So, we see even at start there is a very large torque and there will be a tendency of the motor to start rotating in the reverse direction. Hence, the motor must be disconnected before the speed comes to 0. Thank you.